Okay, good evening, everyone. So, in the last lecture, we were looking at binary representation, particularly of negative numbers, and then we raised a question. One solution is that out of n bits, if I use the first bit as the sign bit and the remaining bits for the magnitude. So that is one solution which we discussed. This is called signed magnitude representation. But there is an issue with this representation, that is you will have two representations for zeros, for plus 0 as well as minus 0. Okay, so this will actually lead to ambiguity and memory wastage. And another thing which we will discuss today, that is to add negative numbers, you need to use a different method than what you use to add positive numbers. So you need two methods. Add negative numbers in the sense subtraction, right? So addition of two positive numbers is addition, but addition of a positive number and a negative number is subtraction. Okay, so for subtraction we need to deal it separately. For addition we need to do it in a different way if we use signed magnitude representation. So what we said, to solve all these problems, we introduced something called R's complement. R's complement is generic to any number system. Specifically, we discussed. I am still getting noise from that direction. If you are not interested, leave immediately. Don't disturb me and other interested students. Okay. So we discussed tens complement, nines complement, but specifically we are interested in twos complement and ones complement. All right. So suppose. So there are three problems which I mentioned, right? One is ambiguity, right? Because plus 0 there is one representation, minus 0 there is one representation. So for 0, but both are same, plus 0 and minus 0. You don't need two representations. So you are wasting space, and then there is ambiguity. If I enter 0, what representation should the system choose? Plus 0 representation or minus 0 representation? Okay. Again, sorry. Yeah. So when I enter 0, how does the system understand whether it should store plus 0 representation or minus 0 representation? So that is ambiguity. Second thing, when both mean the same, why two representations? So that is memory wastage. Third thing, if you use signed magnitude representation to store negative numbers, representation wise it may be fine, but to perform operations, it will not work out. How many of you watched that video I shared on Discord? Very few. What about others? Fine, I am not going to cover that. Either you watch it or you don't. Don't expect every small thing to be covered in the lectures or tutorials or labs, because the course is big. Everything cannot be covered during the contact hours. We share some resources with you so that you will learn some things which cannot be covered during the lectures, etc. So if you don't learn or if you don't watch them, don't read them, it's your loss. We can't cover everything. Okay, I will just touch upon that. And if you are interested, you watch that video. That's all I can say. Okay, so I will explain to you how twos complement will solve each of these problems: ambiguity, memory wastage, and uniform method for addition and subtraction. So let's take an example. So let's take, say, 5. 5 in binary is 101. Okay, suppose I have a 4-bit representation. Then I fill this space with a 0. I may have 8-bit representation, 4-bit representation, whatever. I'm assuming I have 4-bit representation. Okay. Now minus 5 in signed magnitude representation will be, this will be 1, right? Or let me take a slightly larger number so that you will understand what we are. Suppose I take or 5 in 8-bit representation. It requires only 3 bits, but if you are taking 8-bit representation, it requires 5 zeros. 1, 2, 3, 4, 5. So this will be plus 5. In signed bit representation, this will be 1 followed by 4 zeros and then 101. Okay, this indicates positive, this indicates negative, this indicates magnitude. Okay. Now, if I add them, right? If I add these two numbers, I should get 0, right? So let me add them. 1 plus 1. 1 plus 1 is 2. 2 in binary is 1, 0. So here 1 is carry, 0 is the sum bit. Okay. Like in decimal, 9 plus 1 is 10. There 1 will be carry, 0 will be written below. Here 2 is 1, 0. Okay. So here 0 and 1 is carry. This will be 1. Again 1 plus 1, 0 and 1. This will be 1, 0, 0, 0, 1. Okay. So now this one is what? What is this? 9. It's 10, right? So overall this number will be minus 10. Is this the right answer? No. 5 plus minus 5 should be 0. Here we did addition, we didn't do subtraction, right? Here normal decimal addition will give us 0, but here it is giving us minus 10. So we are not getting the expected result. Why? Because this number representation wise it means minus 5, but that same representation you can't use in the same form for addition. So you need to take it as, so you need to remove the sign bit and you need to take the magnitude separately, and then you have to do subtraction as such. Okay, 5 and then 5, you need to perform an operation called subtraction where you need to take carry from the higher order bit like you do for decimal numbers, right? So that's a different operation altogether. Fine, but let's take 2's complement. So how do we calculate 2's complement of 5? 1's complement plus 1. Okay, so 5 in 8-bit representation is 5 zeros followed by 101. So first I need 1's complement of 5. What is that? Just flip the bits. Okay, 1 1 1 1 1 0 1 0. Fine. And then how do I get 2's complement? By adding 1 to it. Okay. So 1 1 1 1 1 0 1 1. So this is 2's complement of 5. So this is equal to minus 5. Okay, in 2's complement representation. Now let's add this 5 and this minus 5. Okay, so let me copy this. And let me copy this. Okay. Now 1 plus 1, 1 0, 1 plus 1, 1 0, again 1 plus 1, 1 0, and you go on doing like this. Here you will get carries, right? Here you will get one more carry. All these will be zeros. You will get a carry. You ignore the carry bit, right? So what are you getting? All zeros. This is what? 0. So you got the right answer? Yes. So you add 5 with 2's complement of 5. You got 0. You didn't change 2's complement of 5. You didn't take it, okay, first bit is sign bit, then this is magnitude. Let me take the magnitude separately, and then let me perform the subtraction operation. No. You performed addition operation only, but of one positive number and one negative number, so it becomes subtraction. Okay, so you don't have two different operations. Here you only have two different types of numbers. Okay, but if you want to do subtraction separately, then either positive numbers or negative numbers, you have to perform addition separately and subtraction separately. So there you have two different kinds of numbers and two different kinds of operations. But here we have two different kinds of numbers, positive and negative, but only one kind of operation. If you add two positive numbers, it will be addition. If you take one positive and one negative, it will be subtraction. You're adding them still. The operation is still addition only, but it is equivalent to subtraction. Fine. So this is giving us the right answer because this particular representation suits well to perform subtraction of two numbers. Okay. Now, how do we say that 0 has only one representation? So let's take 0, 8 bits. What is its ones complement? All ones. How to get two's complement? You add 1 to it. Okay. What will you get? 1 0, again 1. This will be 1 0, 1 0, 1, 1 carry, and so on, right? You will get all zeros here and ones here and 1 carry here. That will come here. Ignore this. What are you getting? You are again getting same representation. So in 2's complement representation, there is no two representations for 0. Plus 0 and minus 0, no two representations. 0 and 2's complement of 0 are identical, which means plus 0 and minus 0 are identical. 2's complement of n is minus n. So 2's complement of plus 0 is minus 0, but both are identical. So space is not wasted. Second thing, then what about minus 0 representation? That is also possible, no? 1 followed by 7 zeros. Okay. What about its 2's complement? First, let's take 1's complement. 0 followed by 7 ones plus 1. Let me use next page. Again 1 plus 1, 1 0, 1 plus 1, 1 0, and so on. Okay, I'll get carry. Here it will be 0, 0, 0, 0, 0, and 1. Again, this is identical to the input. Okay, but what is the corresponding decimal number here? This will be minus 2 power 7. That is minus 128. So let me tell you why. When you have 2's complement of a number, particularly negative number, any number, here the place values go from like 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5, 2 power 6, and this will be minus 2 power 7. So the last bit, this is called MSB, or most significant bit. Okay, this is called LSB, least significant bit. So in 2's complement representation, the last power will be a negative power. So you multiply this one with minus 2 power 7 and multiply these with their respective powers and add. Finally, whatever value you get, that is the value of this number. Okay, so suppose I take 1101 in 2's complement. So this will be 1 into 2 power 0 plus 0 into 2 power 1 plus 1 into 2 square plus minus 1 into 2 cube. Okay, so this will be minus 8 plus 4 plus 0 plus 1. So minus 8 plus 5, this is minus 3. So if this is minus 3, let's take its 2's complement and see, we should get plus 3. Okay, so 1101, first let's take 1's complement, 0010, add 1 to it, 0011. Is it plus 3? Yeah, that's it. So if you take 2's complement of 3, you should get minus 3. If you take 2's complement of minus 3, you should get plus 3. Now, even if you apply the same thing, since this is 0, minus 2 square, minus 2 cube doesn't matter. This will be ignored. These places are all positive places. So you will get the magnitude from these places. Okay, you will understand this a little in a little while. Okay, so this much you understood. 2's complement is good because it will save space. No two representations for zeros, only one representation. And second thing, the other representation for 0. What is this? This is in signed magnitude. This is -0, right? But in 2's complement, this is -2 power 7. That is -128. Okay. So if you have 8 bits in unsigned magnitude, what is the range? What is the total number of values that you can capture using 8 bits? 2 power 8. Okay, that is total number of values. What is the range of values? 0 to 2 power 8 minus 1. If I take signed magnitude, that is 1 bit I reserve for sign, then the range will be minus you don't remember? Minus of 2 power 7 minus 1 to plus 2 power 7 minus 1. So in this case, it will be minus 127 to plus 127. Okay. In 2's complement representation. So why was this minus 127 to 127? The total number of values are still 256, but 0 is taking 2 values. Okay. That's why it is minus 127 to 127. In 2's complement method, the range goes from minus 128 to plus 127. So minus 0, whose space we have saved in 2's complement, that value, that binary representation is given to minus 128. So we got an additional space for an additional number. Instead of minus 0, we got a meaningful number. Okay. All right. You will need to watch that video to understand some of the things which I am discussing. Otherwise, you won't understand. Okay. I won't spend more time on this. All right. So let's do a quick recap of some things. We discussed so far that information, all the information that you can think of, all the information that you want to represent in the computer, finally, it has to be represented in the form of bits only, right? Zeros and ones, binary digits, nothing else. No other way of representing any information. So we discussed different ways of representing the information, like in different number systems, binary, decimal, and then we also discussed number system conversions, binary to decimal, decimal to octal, octal to hexadecimal, and so on. Okay. So once I represent the data, then what next? Once I save the data, store the data, then what do I do with it? Do I use the computer just to store the data? That's it? Huh? So using means what? Just retrieving. Yeah? Huh? Yes, performing operations. Computing. You want to compute something, not just give the data and get back the same data, right? I want the computer to do something with this data I give. So I want the computer to process this information, to do some processing. So whatever you do, right? Different kinds of processing. Any examples? What kinds of processing we make the computer do for us? Addition, subtraction, arithmetic operations. Okay. What else? Logical. Okay. What else? Huh? Sorry? Mining. Finding data, searching. Okay. Yes. What else? So web page searching, that is also like Google search, that is also processing. You are giving a query and it is searching for that query. It is retrieving web pages for us. That is also processing. What else? Many things. Exactly. Everything, every single thing you do on a computer is processing data. You are playing games, you are watching videos, you are playing music, you are using an Excel sheet, you are sorting data, you are doing anything you're doing. You're clicking a button, you're opening browser, you're closing browser. Whatever you do, that is information processing. Okay. And since all information needs to be represented in bits, all information processing finally needs to boil down to bit operations. That's it. Whatever complicated processing you are doing, addition, subtraction, integration, derivation, or machine learning, or playing, or watching something, whatever you're doing, everything needs to boil down to bit operations. That's it. There is no other option. So whatever complicated task you're doing, it will be finally boiled down to binary operations. Okay. Now, can you tell me, or before that, so let me give you an example. So suppose we have an image, grayscale image, black and white. This is information. How is this information represented in bits? Yes, in this case, you need not worry about pixels. It's like a matrix. Yes, it is pixels, but here each pixel is, yeah, it's just zeros and ones. If it is black, say 1. If it is white, say 0. That's it. Now, so this is information. This information I'm storing in the form of bits using zeros and ones. Okay. Now, processing, we can do. You can do different kinds of things with images, right? You can crop them. You can invert the colors. You can do many things. So in this case, we take one example. Say we invert the colors. So in terms of bit operations, what is happening? Yes, you're flipping the bits. That's all. Zeros are becoming ones are becoming zeros. One's complement. Exactly. One's complement of the matrix. You take one's complement of the original matrix, you will get this image. Okay. So this is one example. So each bit has been negated to invert the given binary image. All right. Similarly, all information processing ultimately amounts to bit operations. This is one simple example of a grayscale image. Okay. You can do many things with images, particularly with colored images. You can do many more things, and then many more operations, images, sound, audio, video, anything you take. All kinds of operations you can do. All those operations finally have to boil down to bit operations. Okay. Now, can you tell me any bit operations that you can think of? We just discussed one, that is flipping the bits. That is one kind of operation. Any other operations? That's flipping, inverting. Yeah. What else? Sorry? Coloring an image. Okay. In terms of bits, at bit level, what operations can you think of? Suppose you are given zeros and ones. What can you do with them? What kind of transformations can you make? What kind of operations can you perform on just zeros and ones? Sorry? Algebraic in the sense? Okay, adding, subtracting, arithmetic operations. Yes. But even those are slightly high level. Even bit operations are still low level compared to addition, multiplication, etc. Or let me give you a clue. Suppose you take truth table, true, false, right? So what kind of operations, logical operations you know of? What kind of logical operations can you perform on truth values? And, or, not, implication, by implication, and so on, right? Same thing here. Think of 1 as true and 0 as false. Here also you can perform equivalent operations on bits. So if you have two values, two variables A and B, both of them can be either 0 or 1, and you can perform different operations like AND, OR, NOT, NAND, NOR, XOR. So AND, you know, so A and B will be true only when A is true and B is true. In all other cases, A and B will be false. A or B will be true, or A or B will be false only when both are false. In all other cases, A or B will be true. Even if one of them is true or both of them are true, then A or B will be true. Only if both are false, then A or B will be false. Not A is a unary operation. It will take only one input. All the other operations are binary operations. They will take two inputs, A, B, not A or not B. It is unary operation to take only one input. So here you need to focus only on A. So you just flip the bits. Wherever A is 0, not A will be 1. Wherever A is 1, not A will be 0. Okay. NAND A, NAND B means not of AND operation. So first you perform A and B and then take negation of that. So wherever A and B is 0, A and B will be 1. Wherever A and B is 1, A and B will be 0. Okay. So it's like two operations combined into one. NOR is again not of A or B. Take this column A or B and flip the bits. Okay. What is XOR? Exclusive OR. So what is exclusive OR? Huh? Yeah, why? The name tells us something. What is the name telling us? Exactly. Exclusive OR means, see, again, language, there is ambiguity when you use normal OR in English. It may mean two things. When I say either this or that, it may mean that either A is present or B is present or both may be present. But if I say exclusively only one of them is present, it's like only one should be on, other should be off. Right? That's it. So only those cases where one is true and other is false, only those cases are true in XOR. When both have same values, that is both are true or both are false, then that is false in XOR. One is present, one is absent. So exclusively only one, only A is there or only B is there. Both cannot be there. That's why XOR means only if one of them is true, other is false, then XOR is true. If both of them are true or both of them are false, then XOR is false. Okay. So these are the basic operations. All operations which we discussed so far, all processing which we discussed so far, all examples which we discussed so far, all of them will be finally reduced to these bit operations. That's it. All computation, no exceptions, can be achieved using these binary operations. That's it. No matter how complex your computation is, no matter how many days or months or years your code will run, how complex your processing is, all of them are finally converted to these bit operations only. That's it. Okay. At the low level, this is what is happening. Fine. Now, but how can we automate these operations? How do we implement these operations in a computer on a physical device? How do I say, okay, perform AND operation or perform OR operation? Yeah. Yes, we will see in a while. Like we will see how addition is reduced to these operations. Yeah. How do I perform AND operation physically? How do I tell the computer perform OR operation? Some of you are from ECM. Yes. So you should know, you should tell me. It has something to do with. Yeah, that is fine. That's like I'm giving 0 and 1. High voltage, low voltage. But how do I tell, okay, I'm giving you 1 and 0. Now perform AND of this 1 and 0. Or perform OR of this 1 and 0. Exactly. Logic gates, circuits, right? So how are they actually implemented? Using transistors. Okay, logic gates are conceptual, but physically they are implemented using transistors. So we'll take an example, say of AND gate. So what is AND gate? Here there are two switches and both of them are in sequence. So if you place two switches in sequence or two transistors in sequence, you are getting AND gate. Why? Only if both the switches are closed, the current will flow. If even one switch is open, the current will not flow. So even if one switch is 0, the current will not flow. Only when both the switches are 1, the current will flow. That's it. So how you place the transistors? So how do I now tell me how do I implement OR? Huh? Parallel circuit. This is a sequential circuit. you change it to parallel circuit. So if the current passes through even one of the switches, the current will flow in the entire circuit. That's it. So this is how you implement bit operations. Okay. So this we call as logic gates. These are conventions. These are not how physically the gates will look. They are different symbols given to different logical operations. Okay. So AND gate will look like this, and notation it is not represented like this: A dot B. Dot means AND operation. And these truth tables, these tables you have seen. This is the same table, so I will not again spend time on that. So these are different logic gates. AND gate looks like this, OR gate looks like this, and it is represented as A plus B. And NOT gate looks like this. So whichever has NOT in it, that will have a small circle in front. So NOT has a circle, NAND has a circle, NOR has a circle, but OR does not have a circle, AND does not have a circle. Okay, you take the AND gate and put a circle, you will get NAND gate. You take the OR gate and put a circle, you will get the NOR gate, and so on. Okay, and if you notice clearly, all these gates have two inputs, whereas NOT gate has only one input. Why? Because NOT is a unary operation. It takes one input and gives one output. All other gates take two inputs and give one output. Okay, that's it. Fine. Simple. Now let us see how addition is done in terms of these operations. Okay, so addition, we just saw it is quite simple. So suppose I say 0 plus 0, it is 0. There is no carry, so this carry is also 0. Okay, 0 plus 1, it is 1, no carry. 1 plus 0, it is 1, no carry. 1 plus 1, it is 0 and a carry of 1. Okay, so in all these cases, there will be two outputs. This is called the sum bit, this is called the carry bit. Only in this case, the carry bit is 1. In all other cases, carry bit is 0. Okay, so same thing, 0 plus 0, sum is 0, carry is 0. 0 plus 1, sum is 1, carry is 0. 1 plus 0, sum is 1, carry is 0. 1 plus 1, sum is 0, carry is 1. Okay, now if you look at each of these columns, do they match with any of the bit operations? This column, sum column, does it match with anything? XOR, right? And this carry column, does it match with anything? AND operation, right? So when you are giving two inputs, A and B, if you perform A XOR B, you will get which bit? Sum bit. If you perform A and B, you will get which bit? Carry bit. Okay, so you need to give A and B as input to two gates, XOR gate and AND gate. XOR gate's output will be the sum bit, AND gate's output will be the carry bit. Combine these two, that will be your result. Okay, so sum is A XOR B, carry is A and B. We can add numbers using a series of logic gates. So it looks like this. Full adder I'll just explain in a minute. Half adder is what we discussed just now. So A and B I give as input to the XOR gate, and same A and B I also give as input to the AND gate. XOR gate's output will give me the sum bit, AND gate's output will give me the carry bit. Okay, I combine these two, this will be my output. So 1 0. If both A and B are 1 1, so 1 XOR 1 is, if both are same, XOR will be 0. 1 and 1 is 1. So sum will be 0, carry bit will be 1. That is what we got here, right? 1 plus 1, sum bit is 0, carry bit is 1. Okay. Similarly, you take any other input, you will get 0 1, 1 0, whatever it is, 0 0, you will get the expected outputs. So full adder circuit, it is necessary when we are adding 3 bits at a time. A and B are 2 inputs. Sometimes we need to add 3 inputs. Can you think of a case where we need to add 3 inputs? 3 bits at a time? A plus B plus C kind of a thing? When? That's okay, but why do we need this? Why do we need full adder? No, no, not subtraction. I mean, the figure itself has the answer also. Yeah. To add carry bit also, right? So when you perform addition of two numbers, if there are more than one bit, if it is a sequence of bits, when you are performing addition, sometimes you may get a carry, right? So that carry plus the original bits in the two numbers, all three should be added, right? You can't ignore the carry, no? You have to add the carry also. So for that, you need additional gates. So full adder is considering carry in also, along with A and B. Suppose if I have 1 1 1 and 0 1 1, now what am I doing? Here there is no carry because these are least significant bits. In the first step there is no carry. So 1 plus 1 is 1 0. Now this 3 ones I need to add, right? I can't take only these 2 ones. I can't ignore this carry. I have to add these 3 ones. So what will be the answer? If I add 3 ones, yeah, in binary it is 1 1. In decimal it is 3. In binary 3 means 1 1. So I will get 1 here, I will get a carry here. Again I should add 1 1 0. So that is 1 0. Okay, so here there are 3 bits. Here there are 3 bits. Only here there are 2 bits. Right? So for adding 2 bits, half adder is sufficient. But for adding 3 bits, including carry bit, full adder is necessary. Okay? So I'll not get into details of full adder. You will learn in some course logic gates, which discusses logic gates. So we'll not spend more time on that. So the idea is, if you are adding two 8-bit numbers, this is how it looks. The first one will be a half adder. Okay, because there is no carry bit there. Half adder is sufficient. All the remaining adders will be full adders because you may get a carry bit. All right. So in this image, the carry bit is represented here. Okay. So here 1 is a carry bit. This 1 should be added to this 1 and 0. Again, you are getting a carry bit of 1 here. This 1 should be added to this 0 and 0, and so on. Okay. So full adder adds a carry bit as well as 2 bits, two input bits, and will give you the sum bit as well as carry bit. In half adder or in full adder, the output is only 2 bits, sum bit and carry bit. But in half adder, the input is 2 bits. In full adder, the input is 3 bits. That's all. Okay. So just to perform two 8-bit numbers addition, so much of bit operations, so many bit operations need to be done. Two 8-bit numbers, it's like hardly up to 255. The maximum number using 8 bits is 255. So to add two numbers of which each of them is less than 255, so many bit operations need to be done. Okay, now just imagine what if we want to add or multiply or do other operations on a 32-bit number or a 64-bit number. How many bit operations, how many thousands and millions of bit operations need to be performed? Okay, so this is what is happening at the back end at a low level. All right, now you will understand. So this is a circuit, this is an addition circuit. This is a circuit which does addition of two 8-bit numbers. Now you will understand why 2's complement notation is necessary or useful. Using the same circuit, you can also perform subtraction. How? If the first number is a positive number and the second number is a negative number, just by adding these two numbers, you will do subtraction. So you need not change the circuit. Circuit is remaining the same. Using the same circuit, you are performing addition as well as subtraction. But if you use any other representation like sign magnitude representation or 1's complement representation, you can't just add a positive number and negative number to get the correct result. You will not get the correct result. You need to take the sign separately, magnitude separately, and then understand, okay, if it is a negative number, then I need to perform subtraction. If it is a positive number, then I need to perform addition. So I'll have a separate circuit for addition. I'll have a separate circuit for subtraction. It will increase memory and space, everything in the computer. Different circuit for addition, different circuit for subtraction. That is too much. But here, using 2's complement, using the same circuit for addition, you are performing addition of positive numbers as well as addition of positive and negative number, which is equivalent to subtraction. Okay, so that is the greatest strength of 2's complement. So these are the three different representations which are important conceptually. In a computer, only 2's complement notation is used, not sign magnitude or not 1's complement. Okay, so if you look at these three representations, all the positive numbers have the same representation, identical representation in all the three cases. Okay, you take plus 127, same representation, plus 3, same representation in all these. Where does the difference come? When you get into negative numbers. Minus 1 is represented in one way in signed magnitude. You just take the you take plus 1, flip the sign bit first 0 to 1, you will get minus 1. Okay, minus 1 is represented in a different way in 1's complement representation, flipping the bits of plus 1. In 2's complement, it is represented in a different way. Flip the bits of plus 1 and add 1 to it. Okay, so there are different representations for negative numbers. Now, which of these representations is most useful in the sense that I need not worry about different parts in the representation, what is sign, what is not sign, and should I take the magnitude separately and perform subtraction separately. I need not worry of all these things. Whether it's a positive number or a negative number, I will just add and I should get the correct result. That is possible only in 2's complement representation. Okay, and another thing is in sign magnitude as well as 1's complement, you have two representations for 0. Okay, but in 2's complement, there is only one representation for 0. So there is space for one more number. So that one more number is minus 128. Okay, so minus 128 is not present in sign magnitude or 1's complement representation because that is taken by minus 0. That place is taken by minus 0. That memory is taken by minus 0. So one less number. But you have only 1 0 representation in 2's complement representation. So that memory is used for an additional number, additional negative number. That is why the range of 2's complement is minus 128 to plus 127. Range of 1's complement is minus 127 to plus 127. Range of sign magnitude is minus 127 to plus 127. If it is an 8-bit number. Okay. So if you want more details, you should watch that video. By using 2's complement, we have one extra number and one less 0. Okay, this is one advantage. The second thing is, main thing is, we can use the same circuit for both addition and subtraction. We don't need a separate circuit for addition, separate circuit for subtraction. Same circuit we can use for both addition and subtraction. Okay, because in this case, we are using one kind of operation and two kinds of numbers, positive and negative numbers, but operation is only addition. But in other cases, we need to use two kinds of numbers and two kinds of operations, positive and negative numbers, as well as addition and subtraction. Okay, so that is the difference. I won't spend much time on this. You have to watch this video. I gave the link here also. I gave it on Discord. Check this video for more details. Okay, now, so this is the overall low level representation and low level processing understanding of whatever is happening in the computer. Okay, you have data as well as processing the data. Data is finally converted to bits, as well as once you convert to bits, all the high level operations are also converted to bit operations. So not only the information is reduced to bits, all the high level operations are also reduced to binary operations. Okay, so both these things are happening. So this is like a complete picture of what is happening in the computer. Whatever you are giving, high level commands which you are giving, they need to be finally converted to low level binary information as well as low level binary operations. Okay, so this we discussed. Another example, what if color change? Okay, again, this also needs to be converted to binary operations. No other option. But here, in both the cases, there is some kind of human level logic. We are thinking, okay, yellow is changing to green, and only the portion of the flower is changing. Only that color is changing. The remaining color is remaining as it is. So we are thinking in these terms. We are thinking in terms of color. We are thinking in terms of objects. Only the object's color is changing. The surroundings color is not changing. So we are using concepts, very high level concepts like object, surroundings, color. Okay. So these kind of concepts we are using. But none of these concepts the computer understands. It only understands bits and bit operations. So someone needs to convert my high level concepts and my high level instructions into low level data as well as low level operations. Okay. Who does that or what does that? We discussed this in the labs. Compiler. Exactly. Program is what I write in a high level language. It can be C, Python, Java, whatever it is. That is a high level language. Computer doesn't understand that because it still has some English words or keywords like, you know, for, while, or whatever, int or define or a function, whatever. These are words which computer doesn't understand, right? Someone needs to translate this into zeros and ones. Okay. And also when I say add or multiply, these are operations which again needs to be translated into bit operations. Again, that also is done by compiler. So that is exactly what a compiler is doing. It is translating high level instructions given in high level programming language into a low level instructions in low level machine language. Okay. Only then a computer can understand and a computer can execute. So whatever you see as a .exe file in Windows, what do you do? If you want to install something or if you want to run that, you double click on it. But what is .exe file? That is a binary file. That is a machine language code. And how did someone generate that? Basically, someone already wrote a program in some high level language, then they compiled it to get this .exe file. So only this .exe file can be directly run by a computer. If you give a C file or a Python file directly to a computer, it will not be able to run it without you compiling it. Okay, you need to convert it to machine language. Only then a computer can run. Okay, so compiler is the translator which translates high level programs into low level programs. Okay. So when we write a computer program, if you know how to solve a problem, that means you have a logical sequence of steps in your mind to solve it and translate the sequence of steps into a programming language, any programming language, high level. Now the language compiler, if it understands your program, that is if your program has no errors, it will convert your program to an executable, which is a set of machine level instructions. Okay, in machine language, they will be in machine language. This executable lies on the hard disk of the computer. When you execute it, either by double clicking in Windows or by running /a.out in Linux, it gets copied to the RAM of the computer. The executable will take input and gives an output through the IO devices. So this is the black box. All the operation, execution, information processing is happening like this. You're giving a program. That program, even to execute that program, there should be some other program which translates your high-level program into a low-level program. Okay. This low-level program will now act as a black box, which takes an input from you and gives an output. Okay, so that is what is happening. Now, so this is the complete picture of the relation between high-level and low-level processing computation in a computer. Okay, from now, you need to keep at the back of your mind, whatever you're doing at high level is finally being converted to bits and binary operations. From now, we will not explicitly discuss binary operations. We will focus on high level operations. Okay, so what kind of functions or data structures that you can use in a programming language, we will be focusing on that. But at the back of your mind, you should always know that they are converted to bit operations. Okay, so in C, there are 6 kinds of operators. This is true for most programming languages: arithmetic, relational, logical, bitwise, assignment, and miscellaneous operators. Out of which today we will quickly discuss arithmetic and bitwise operators, because we just discussed bit operations. It will be easier for you to understand bitwise operators. Arithmetic operators are quite easy. They are your normal understanding of any arithmetic operation: addition, subtraction, multiplication, division, same thing. And modulus is remainder. Like this is there in maths also. N mod m means whatever remainder you get after dividing n with m. Okay, so if you want quotient, you do n divided by m, you will get the quotient. If you want remainder, you do n mod m, you will get the remainder. Okay, and for minus, there are 2 different cases. One is unary negation, another is binary negation. Unary negation means, suppose I have, say, number 4. Now I want to use -4. Say I want to multiply, say, -4 into 3. So here -4 is negative number. That's all. It's not subtraction as such. It is a negative number. So this is a unary negation, which means it takes one number and negates it. Minus of -4 is 4. Okay. So minus, the symbol is same, but its meaning is disambiguated depending on the context. If minus is put before a number, it means it is negation. It is unary negation. If minus is put between 2 numbers, it is subtraction. Okay, so depending on the context, its meaning changes. This is called operator overloading. Same operator, can be given more than one meaning depending, and this meaning can be teased out or disambiguated based on the context. Okay, so these are basic arithmetic operators. You will do some programs in the labs, so I won't spend much time on it. Let's quickly look at bitwise operators. So these bitwise operators are in line with the bit operators which we discussed earlier, and, or, not, okay, XOR. So these are same, and then there are additional two, right shift and left shift. So we'll quickly see how bitwise operators can be used in regular programming with regular numbers. So far, the bitwise operators we saw, they are dealing with only zeros and ones. Okay. Now I will perform, say, AND operation on some normal decimal numbers. It can be larger numbers also, like 27 and 35, anything. Here there are examples given. You can later look at those examples. Say A is 237, B is 174. So 237 and 174. I will not take that big numbers. I'll take small numbers. So 5 and 4. I want to perform bitwise AND. What do? First, I represent 5 in binary. That is 101, 4 in binary. 100. Now 5 and 4 means you perform bitwise AND with each bit corresponding bits. 1 and 0 is 0. 0 and 0, 0. 1 and 1, 1. What decimal number is this? 4. So 5 and 4 is 4. Okay. Similarly, 5 or 4. Or is represented like this. So 5 or 4. Okay. So 5 again, it's 101. 4 is 100. Again, do bitwise OR. 1 or 0 is 1. 0 or 0? 1 or 1? What is this? 5. So 5 or 4 is 5. Okay. Bitwise XOR. Again, 101, 100. 1 XOR 0, 1. 0 XOR 0, 0. 1 XOR 1, 0. This is 1. So 5 XOR 4 is 1. Complement of a number. It will take only one number as input. It is a unary operator. So I will say complement of 5. What is this? This is nothing but 1's complement. You take 101. I mean, you take 5. That is 101. So complement of 5 will be 010. What is it? 2. Okay. And so on for any number. Now if I want 2's complement of 5, what do? Plus 1. So if I want to calculate 2's complement of 5, in my program I write 1's complement of 5 plus 1. That is 2 plus 1, that is 3. This, if you remember, this is 8 minus 5. Why? Because 8 is 2 cube. You remember R's complement formula, R power n minus n. So if you take 2's complement of 5, you will get 3. So same thing you are getting here. First take 1's complement of 5, add 1 to it, you will get 3. Okay. Now you may wonder, okay, what do I do with these bitwise and bitwise operators with normal regular numbers? Take a problem as homework. You know how to find whether a number is even or odd in any programming language? How? Yeah, you can say, if I have n, how to find if n is even or odd? One way is n mod 2. If n mod 2 is 0, it means n is even. If else, n is odd. Okay. But without using modulus operator, also you can find whether a number is even or odd. Okay. So the clue is, given a binary number, just by looking at the binary number, can you tell whether that number is even or odd? You need not convert it to decimal. Just by looking at the binary number. How? 2 power 0. Units place should be 0. If the last bit, so like you saw here, 5 is odd because last bit is 1. 4 is even, last bit is 0. You take any even number, last bit will be 0. You take any odd number, last bit will be 1. You need not find the entire number value. Okay. Now given this clue, use bitwise operators to find given n, if n is even or odd, using only bitwise operator. Okay. This is your homework. But before we leave, let me quickly tell you right shift and left shift. Suppose if I have 100, what is this? Number 4. if I do, so let's assume I have infinite number of zeros here. It doesn't matter how many zeros I have. If I perform 1 0 0 left shift by 1, okay, which means this 1 will move left, this 0 will move left, this 0 will move left. There is an additional empty space, there 0 will come. Okay, so 1 0 0 on left shift will become 1 0 0 0. What is this? 8. Now this again on left shift will become what? 1 4 zeros. This is 16 and so on. Okay, so 4 is becoming 8 on the left shift, 8 is becoming 16 on the left shift. Suppose I take 1 1. What is this? Number 3. If I do a left shift, this will become 1 1 0. What is this? 6. Again, if I do a left shift, what is this? 1 1 0 0. What is this? 12. Do you see a pattern? What is happening? It is becoming double. So if I take n, if I do a left shift of it by 1 position, what will I get? 2n. Okay. If I do right shift of this, left shift of this 2 times, 4n. If I do left shift of this 3 times, 8n. If I do left shift of this k times, two power k times n. It is 2 power 1 n, 2 square n, 2 cube n. So if I left shift it k times, it will be 2 power k n. Similarly, suppose if I start with 8, if I do a right shift, which means this last bit is erased, what am I getting? By 2. So this is 4. If I again do a right shift, this right bit is erased, I am getting 2. Again, if I do a right shift, this bit is erased, I am getting 1. So if I have n, if I do right shift by one time, what am I getting? N by 2. If I do right shift 2 times, n by 2 square. If I do right shift k times, n by 2 power k. Okay. So if you want to do quick multiplication or division operations by 2, it is better to use right shift and left shift rather than regular multiplication and division arithmetic operators. Bitwise operators are the fastest. If someone asks you in interview or whatever, if you can make this program faster, always think if you can use bitwise operators instead of other operators. Okay, so these will be covered in the tutorials and next week's labs. Okay, all right.